Hello. Today we shall speak about a new concept, which is the concept of differentiation. And this is mainly the main, I may say, the main idea behind teaching calculus, differentiation and then integration. Now, if we follow the footsteps that we did before, we started by limits, studying the limits first, and then limits led us to continuity, and from continuity, now we pass to differentiation. Why? Because a function cannot be differentiable unless it is continuous. And continuity, we now established the continuity of functions. Now, if the function is continuous, then we can move forward to see whether it's differentiable or not. Now, differentiation means, in the language of engineering, to be able to calculate the slope of the tangent at a point. Whereas other specialists or in other specialization, people use the word rate of change. Now, the rate of change, economists use it as well, but they use it under different vocabulary. They call it, for example, marginal cost of production, as we said before, or for example, the elasticity of demand, which is equal to a ratio between the percentage increase in the quantity demanded divided by the percentage increase, for example, in the price. And it is negative because the higher the price, the lower is the demand. So it reflects the response of an individual searching for an object based or to the change in the price. And as well, they have also something called the propensity or the marginal propensity to consume. So they have a different vocabulary, but it amounts to the same thing. Now, in this lecture, we shall focus on the subjects of differentiation. And first of all, we have to define the derivative. The derivative, this is the language that mathematicians use for the rate of change or for the marginal change, like they say in economics. Now, but in mathematics, we call it the derivative. And then the differentiability on intervals. Then we move to the differentiation laws. And then the derivative of basic function, the function that we dealt with before, and we exposed them. And then we use differential. And differentials were the notation that you use by Leibniz. We said that there was a German mathematician in the late 17th century and beginning 18th century. He was contemporary to Newton. And it was these two mathematicians that they discovered the theorem, which is very important, called the fundamental theorem, and which made a revolution in calculus because in the past, to calculate differentiation and integration, especially integration, it was a tedious job, but now by their theorem, it became much easier. But calculus, but also Leibniz is accredited with using a set of notations called differentials, which facilitates even more the algebraic operations of calculus and transform calculus from analysis almost to calculations, and this is why it was called calculus. And especially when you say calculus, you mean calculus of Leibniz. So first of all, we have to define the meaning of a derivative. Now, the derivative of a function, for example, if you have, for example, a relation of this sort, something which increases. For example, you have temperature and time. You have, for example, at t equal, here you measure in second. When t is equal to 1 second, you have temperature 3 degrees Celsius. When it's equal to 2, you have 6. When it's 3, it is 9. Then you say that the temperature increases at the rate of 3 degrees Celsius every second. How would you do this? What you do is that you have a quotient. The differentiation here, or the derivative, is equal to a quotient. The difference in the temperature divided by the difference in time. So you have, for example, 0 and 3. So 3 minus 0 is 3 divided by 1 second. You get 3 degrees Celsius every second. Or you may say 6 divided by 2, which is the same. Or you may have 9 minus 6, which is 3 divided by difference in time, which is 1. So again, it's 3. Here, the relation is linear. And this is special relation. You have a constant rate that you, here, in this case, of increasing the temperature. And the same thing, for example, when you have a relation of this sort. For example, when you have, you have For example, you work in a factory and your boss tells you, for example, you start, for example, your salary by 1,000 euro, and each year you will have a raise of 100 euro. So the first year your salary becomes 1,100, the second year becomes 1,200 euro, etc. So you notice here that if you draw here your salary against the number of years, so and you wish to calculate the rate at which your salary is raised, you can say directly that it raised at the rate of 100 euro per year. How you calculated this? You subtract 1,100 minus 1,000 divided by 1 year, so you get 100 again, or 1,200 minus 1,000, minus 1,100, you get again 100 euro, and you subtract the year, second year minus first year, you get also 1 year, so again you get 100 euro per year, etc. So this is again a constant rate. But it's not the case. This is not the case all the time. You may have a different kind of relationship. For example, you may have, for example, what's called in economics the marginal propensity to consume. What is that? It means that this represents a relation or a ratio between the change in the individual consumption or spending divided by the change in the income or the increase in the income. For example, a family, for example, for each 1 extra euro, for example, of income it receives, for example, if the marginal propensity to consume is, for example, 0.65, because it always lies between 0 and 1, then it means that it spends 65 cents and it economizes 35 cents if the marginal propensity to consume is 0.65, as I said, because it lies between 0 and 1. So this quantity here, of course, it's not linear. Why? Because when your income is low, you tend to spend more. But as your income becomes larger, your needs are satisfied, and you economize more. And therefore, it is not a linear relationship. And most of the relationship in nature are not of the type that are linear. Most of them, very few of them, only are linear. So what we usually have is that we calculate the rate of change. This is now the rate of change, irrespective of the relationship between two variables. You have two variables now. You have variables called x in the domain of the function, and you have another variable y, which is a dependent variable on x. In other words, you assign a value of x and you calculate the value of y, and then you draw the relationship between x and y. If you have a change in x and you measure the incremental change in y and you divide the two, this is what is called derivative of your function f at this particular point. Now it changes all the time because the rate, as I said, is not constant. It depends at the point at which you calculate, for example, like in the general propensity, the marginal propensity to consume. It depends on your income. In other words, it depends on the point at which you seek to calculate your derivative. So, and this is why they call it the instantaneous rate of change of your function. How do we calculate it? You have a curve here. This is a curve. Y is equal to f of x, and you wish to calculate the derivative at the point x equal to a. So it's equal to what? As I said, the slope of the tangent at this particular point. It's irrelevant which terminology you use, the rate of change or the slope of the tangent or the derivative. We can stick to the derivative because since we are teaching mathematics, we shall be using this all the time. So the derivative is equal to what? To the tangent of this angle here. What you do is that you start by taking, for example, from this point, you change, you have this point is A, so you change another point which is equidistant from A by a distance equal to h. H is a fictitious parameter that you take. It could be small, it could be large, it's immaterial. The problem is that h, for example, is positive, and you move to another point here. Now, if you measure the difference in y divided by the difference in x, here you have f of a, and here at any other point x you have f of x, you subtract f of a from f of x, you get this small increment here. You divide this by the difference between x and a, which is x minus a, and this gives you what? Gives you the tangent of this angle. This is the tangent of the secant. In other words, the tangent of the angle of inclination of this secant on the x-axis. The incremental change in y divided by the incremental change in x. But then this depends on the particular value of x. If you choose x here, You get a higher tangent. The more you move x here, it's different. Each time you get a different quotient. So what mathematicians said, now the derivative is something else. The derivative is the angle of inclination, the tangent of the angle of inclination at the particular point A at which you seek to determine this derivative. In other words, the slope of the tangent here. So how can you get a tangent here? Unless this point here moves until it meets with the point P. In other words, you take the limit. So now you can define the derivative at the point A, which is the limit of the quotient f of x minus f of a divided by x minus a, and you take the derivative when x tends to a. Now here you realize something. You realize that both the numerator and the denominator, they tend to 0 simultaneously. And this, as a matter of fact, Newton in the 17th century, he knew this, but he couldn't express it in the form of limit because limit didn't exist yet. It was only in the late, after one almost century, that the limit was intervening in calculating derivatives. But anyway, here the numerator tends to 0. Why? Because the limit of f of x when x tends to a is equal to f of a from the continuity of f at the point A. Because you should first, at the beginning, make sure that the function is continuous at the point A before indulging any more or before going further and proceeding to calculate the derivative at this point. If the function is not continuous at the point x equal a, then there is no point of calculating the derivative. So you divide these two and you take the limit, and this you get the derivative. Now, if you can use also another form, you can, for example, take x is equal to a plus h, and you can use another formula. This is, you substitute x by a plus h, and this is another way of calculating the derivative. These are two similar expressions for calculating the derivative. If the derivative exists, if this limit exists, then the derivative exists at the point A. Now here, for example, calculate the derivative. Take a very simple example. You have here a parabola, and you wish to calculate the slope of the tangent at the point x equal to 1, i.e. the derivative of the function at 1. So you can use either expression. It's irrelevant. Which expression suits you, you can use. For example, we use the first one. So you take the limit when x tends to 1 of f of x, which is x squared, minus f of 1, the value of x squared at 1, which is 1, divided by x minus 1, and you take the limit here directly. It's the limit of the same function x plus 1, because you decompose the numerator, and you got 2. So 2 denotes what? The slope of the tangent at the point x equal to 1 on the graph of the function y is equal to x squared. There is one important thing I wish to draw your attention, is that if you want to calculate, and this is important, the slope of the tangent at a point, you have always to use this expression at this point. You cannot calculate the expression, the derivative at any point and then take the limit. This you can do provided that the derivative itself is continuous, because you want now to take the limit of f dash of x when x tends to a to be equal to f dash of a, which you seek to calculate. Now you cannot do this unless limit of f dash when x tends to a is equal to f dash of a, which means that f dash must be continuous at the same point. So if you want to calculate the derivative at any point, you can do whatever you want. But if you want to calculate the derivative at a particular point, then you have to do the first principle, and they take the limit at this particular point of this expression. And this expression tells you what? Tells you that this function is not defined at the point x equal to 1. Yet this limit is the derivative, and this you have to take it into consideration. Now, suppose, for example, you have this function x squared, and you wish to calculate the derivative at the point x equal to 1. So what we do is that we take the limit of this expression. This is the limit of this expression, gives you what? When x tends to 1, gives you the derivative at the point x equal to 1. Now, this gives you what? It's a function which is not defined at the point x equal to 1. And this is important. You are not taking the limit of the function, but you are taking the limit of another function which is not defined at the point at which you want to calculate the derivative, yet its limit, when it exists, gives you the derivative. So here, what you do, each curve, this line here, coincides with the function which is not defined at the point at which you want to take the derivative, but its limit at this particular point gives you the derivative, which is 2. Now suppose you want to take the derivative at the point x is equal to 2. So you consider another function, which is x squared minus 4. This is the value of f of x squared at the value at x equal to 2. So this is another function, which is again undefined at the point at which you seek to determine the derivative, which is x equal to 2. But then when you take the limit, when x tends to 2, it gives you the derivative. So here, this is the other function, and the derivative, in which case it's equal to 4. So that the slope of the tangent at the point x is equal to 1 is equal to 2, and the slope of the tangent at x is equal to 2 is equal to 4. Now what about the slope of the tangent for any value of x? So what you do is that you connect these points and you get the slope of the tangent at any point x of the curve of the function f, which maps x into x squared. So the slope of the tangent at any particular point x on the curve y is equal to x squared is equal to 2x. And therefore, and for any function x to the power n, the derivative becomes n x to the power n minus 1. His n is 2, so you get 2 times x to the power 2 minus 1, which is 2x. And this is the derivative at any point x on the curve y is equal to x squared. Now this is an important theory. We shall not be waiting long for it, but we wish to emphasize a point here, is that a function is differentiable only if it is continuous. In other words, a differentiable function is continuous all the time. A differential function, you are sure, since it's differentiable, then it is continuous, and the proof is very simple. You take the limit here of fx minus f of a, but since both exist, because the function is differentiable, because here you cancel out x minus a, so this is equal to this, but the limit of a product of two functions is equal to the product of the limit, since each exists. Now here, the limit exists because the function is differentiable. So this becomes equal to the limit of this times the limit of this. When x tends to a, this becomes 0. So you get this equal to 0. But this means what? That the limit of f of x when x tends to a is equal to f of a. In other words, the function is continuous. So a differentiable function at point means that it is continuous at this point. But the contrary, unfortunately, is not true. In other words, we find functions that is continuous everywhere, but it is not differentiable. And if you remember our first introductory lesson, we saw a function that was designed by this German mathematician that was continuous everywhere and differentiable nowhere. So this particular function here, which is mod x, this function is continuous everywhere and differentiable everywhere except at this particular point, which is x equals 0. How can we prove this? It's easy. All you have to do is to take the limit at f dash of 0. You use the first principle. Here, what you realize something here, to calculate f dash at this point here, at any point for x greater than 0, it's equal to 1 because the angle is 45 degrees. And here it's 135 degrees, so the derivative is minus 1. Whereas at the point x equal to 0, we take the limit of what? Of f of 0 plus h minus f of 0 divided by h, and you got a function like this. Note something, that this function here is the function used to calculate f dash of 0. So for each particular point, there is a certain function of h which you seek to calculate the limit of this function. Now this function, if you want to draw it, this is not the function of the derivative. It's the function of h, of which the limit of which gives you the derivative of the point x equal to 0. In other words, for every point, again, like the preceding example, for every point you have a certain graph of h or a certain graph of x, and this graph is not defined at this particular point in which you seek the derivative, but at the same time, when you take the limit, you get the derivative at this particular point. So now this is a curve of h, and you directly notice here that the limit of this function, when we saw this before, mod x over x when x tends to 0, this function here has no limit at h tends to 0. It tends to 1 from the right-hand side and minus 1 from the left-hand side. Therefore, the function is not differentiable at the point x equal to 0. So although it's continuous at the point, but it's not differentiable. Now we come to an important theorem. The theorem which tells you when is a function differentiable at point. Now here it's equal to minus 1, and from the left and from the right is equal to 1. So they are not equal, and therefore we can arrive at this important theorem. A function has a derivative f dash of a at a point a if and only if the derivative from the right-hand side, this is called the left-hand side derivative, and this is called the right-hand side derivative. If they are equal, then the function is differentiable at a point and f dash of a exists. If they are not equal, and therefore if one exists and the other one not, then the function is not differentiable at this particular point. So all you have to do is that to check the limit of a certain function of h. If it exists, then the function is differentiable. If it is differentiable, as I said, then it is continuous. Now, if you want to check f dash of x for any value of x greater than 0, you have another function. And here, if you do your exercise here, you take x positive. This is the same function we dealt with before, except that x is not 0. If you take x is 0, what you end up with? You end up with a function which has no limit. And this is why we reached the conclusion that the function is not differentiable at x equal to 0. But for when x is greater than 0, you find that here you end up with 1. In other words, the function is differentiable for x greater than 0, and the derivative is 1. because the slope is equal to 1. And if you do the same thing for x less than 0, you find it equal to -1. And therefore, what you can say that your function, now this is the derivative of the function mod x. When x is positive, the derivative is 1. When x is negative, the derivative is -1. But when x is 0, the function has no derivative, although the function is continuous at that particular point. And if you want to do the same exercise to calculate the derivative at any point x, whatever this value of x be, positive, negative, or 0, what you do, you can follow the basic principle that we did before, and I leave this as a slide here. It tells you how you do it, and we did the same thing, except that you leave it for any value of x, and you end up with what? You take the limit, and you multiply by the conjugate. This is a trick that students do until you end up with x over modulus x, or same thing, modulus x over x, provided that x is not 0. And therefore, the derivative of mod x, or absolute value of x, in general, it's equal to what? It's equal to 1 where x positive, -1 where x negative, and does not exist at x equal to 0. So we can generalize this by saying that the derivative is equal always to mod x over x, which is equal to 1 for x positive, -1 for x negative, and you exclude the value x equal to 0, or the point x equal to 0. Now, as I said, when a function is differentiable, then it is continuous. But continuity does not imply differentiability, and we saw the case of corner point. But this is not the only case. There are other cases in which the function is continuous and it's not differentiable. So mathematicians try to, like in case of continuity, they try to classify the type of discontinuities. Here also they try to classify the kind of functions that are continuous and they are not differentiable at a point. For example, this we call a corner point, because the curve comes like this and then it turns, like you have a street and you turn in another direction. So this is called a corner point. This is called a cusp, where it's here you have the tangent slides to -infinity from the left-hand side, for example, and from the right-hand side, it goes to infinity. So it turns abruptly from -infinity to +infinity. This is called a cusp. Whereas you can have a vertical tangent. Both you approach infinity from both sides. But you have here a vertical tangent. Here the tangent becomes, the slope is equal to infinity, but it goes to infinity from both sides, or to -infinity from both sides. So these are the type of continuities of the function that at which the function is not differentiable. Obtain the derivative of 1 plus x. This is a function here. 1 plus x, you have for x greater than 0, and x when x less than 0. Now this function here is defined for x equal to 0 and it's equal to 1. Since it is not continuous, then there is no point of, at the point x equals 0, there is no point of calculating the derivative. It won't exist, of course. But yet, when you realize here, you realize that the derivative here is equal to what? Is equal to 1. You can differentiate this directly and gives you 1. And from the left-hand side, it's also 1. So the function, as a matter of fact, if you wish to draw the derivative as a function of time, the derivative when x is greater than 0 is 1. And when x is less than 0 is 1. Of course, you can follow the basic principle. And these are the results. I'm not lying to you. Of course, you can take the limit, and from x tends to 0 from the right and from the left. You'll find that here it's 1, and here it's 1. Yet at x equals 0, there is no point of calculating the derivative. Why? Because the function is not continuous at x equal to 0. But the thing is, which is important, you realize something. You realize that the limit of f dash of x, when x tends to 0, is 1. In other words, when you calculate f dash of x at any point, x positive or x negative, and then you take the limit, you will find always that the limit is equal to 1. So yet the function f dash of x, which is the derivative, has a limit as x is 0, yet f dash of 0 does not exist. And this tells you an important thing. It tells you that you never take the derivative at any other point, and then you take the limit of the derivative when x tends to the point at which, the particular point at which you seek to determine the derivative. You have to calculate it from the very beginning at this particular point, and you don't take the limit of f dash when x tends to this point. Why? Because you are not sure if f dash is continuous or not at this particular point. And here, in fact, f dash is not continuous because it does not exist at x equal to 0, and yet it exists on the right and left side of this point. So its limit is 1 all the time. Here it is. I calculated them. I don't remember, but now here it is 1 and 1. So it tells you that the limit of f dash is equal to 1, yet f dash at 0 is not equal. It does not exist, and therefore you cannot rely upon this expression here in order to calculate f dash of 0 because it does not exist since the function is not continuous from the very beginning at the point x equal to 0. And there are other, as a matter of fact, situations which is the contrary exactly. In other words, you may have f dash existing at a point, yet the limit of f dash does not exist at this particular point. And this is the same kind of problem. Again, it is the contrary of the one preceding it, the one before. The other one, limit f dash exists, yet f dash of 0 does not exist. Here, the contrary happens that f dash exists at x equals 0, yet the limit does not exist. But in either case, you cannot rely upon the limit of f dash, and that's the conclusion that I'm drawing. You cannot rely on the limit of f dash at any point and take the limit to the point at which you seek to calculate the derivative. In order to calculate the derivative at this particular point, you have always to seek the derivative from the first principle at this particular point, which you are interested to calculate y dash or the derivative. Now we come to some conclusion here. These are questions that are nice to answer. If f is continuous at A, is it differentiable at A? Of course not, like model SS, for example. If f is differentiable at A, is it continuous at A? Of course. This we proved. If f is differentiable at A, does the limit of f exist at A? Of course, because if it is differentiable at A, then it's continuous at A. Then the limit of the function exists and is equal to f of A. Now, if f is differentiable at A, does f dash is continuous at A? No, like the last example, f dash is not continuous at A because f dash has no limit at the point A. Now, if limit f dash exists at A, then f is differentiable at A? Of course not. This is the example just before the last one, because the limit of dash was equal to 1 and the function was not differentiable at A. Now you may have also, like continuity on interval, you may also have a differentiability on interval. How? The same thing exactly. We remember the continuity that you took the limit. Here the function is differentiable on the open interval, and if you want to check the differentiability on the closed interval, you do the same thing exactly like the inner points, the interior points of the interval, except that you take the limit from the left-hand side from A, from the right-hand side, I'm sorry, in A, and from the left-hand side of B. So here, f dash of B, if f dash from the left-hand side of B, it's called the derivative from the left-hand side at B, which is the same, use the same expression, but you take the limit when h tends to 0 from the left-hand side. Whereas at A, you take the limit when h tends to 0, approach 0 from the right-hand side. If both exist, along with that the function was differentiable on the open interval, then you can say that the function is differentiable on the closed interval from A to B. Here it is. We call these half tangents because there is no tangent. The function does not exist from the left-hand side from B here, with x less than B does not exist, and therefore you have half tangent here and half tangent there, and they both exist, and therefore the function is differentiable on the closed interval. And of course, since it's differentiable on the closed interval AB, then it is continuous on the same interval also. Now we have some, each time we don't have to resort to differentiation law, you don't have to resort to the first principle in order to calculate the derivative of a function. You can resort to some laws called differentiation laws. And these are simple, very simple theorems. For example, you have two functions, f and g, that are differentiable. Then, of course, the sum is differentiable. The product is differentiable, and it's equal to the product of the first time the second, plus the first time the derivative of the second. Or, for example, you have the quotient of two functions, and you wish to calculate the derivative, then it's equal to a quotient of the derivative of the numerator times the denominator without differentiation, and you subtract from it the first function, which is the numerator times the derivative of the denominator divided by the denominator square, provided it's not equal to 0. And these are laws that you always use to calculate derivative of functions. Now we come to the derivatives of basic functions, which are the functions that we have exposed and studied them before. We give the list without proof because you find them in any textbook, as a matter of fact. But we shall deduce one, for example. Let's say we want the derivative of sine x. What we do, you use from first principle the law that we've used it before in the first slides. You take the limit when h tends to 0 of sine x plus h minus sine x divided by h. If this limit exists, then the function has a derivative and you wish to calculate. What you do is that you remember in the basic functions, we used to know the sine of the sum of two angles. So sine x plus h is equal to sine x cosine h plus cosine x sine h, and you subtract sine x divided by h. Now what you can do is that you can take, for example, these two quantities together, and you take this one, you isolate this one. So here you have what? You have sine x common, and you take the limit because this is not function of h, so you take it outside. The limit when h tends to 0 of cosine h minus 1 divided by h, plus what remains here, cosine x times the limit of sine h over h. And we said before, remember, in the limit theorems lesson, we said that limit sine x over x when x tends to 0 is 1, and the limit of cosine x minus 1 divided by x is 0, so this becomes 0, and this becomes 1, and you end up with cosine x. So now that we are sure that the sine x, which is a function that has a domain R, the derivative of sine x at any point x is equal to the cosine of the same angle here, and this is one knowledge that we should memorize. So now you have all the functions in detail. The derivative of x to the power n for any n is equal to n times x to the power n minus 1. For example, you have square root of x, so the derivative is equal to what? Half times x to the power minus half. In other words, 1 divided by 2 square root of x. The derivative of a to the power x, if it is e, then it's easy. You got e to the power x. But if it is a, then we multiply by ln a. Here is the derivative, the one that we've just calculated. Derivative of sine x is equal to cosine x, and you have the rest. You can find them in any text. Again, the sine hyperbolic. Look at the resemblance, and this is why I'm telling you this before, that hyperbolic function resemble very much in terms of algebraic laws trigonometric functions or circular function. And this is why the derivative of sine is cosine, and here the derivative of sine hyperbolic is cosine hyperbolic. The difference in cosine, there the cosine function, the derivative is minus sine, here it is sine hyperbolic, and this is why they are exactly the same in every respect, except for you add up the hyperbolic, the term h or the symbol h again, and you change the sign whether it's positive or negative. For example, this is, you want to use differentiation laws, dy by dx of this expression. So what you do, the derivative becomes equal to what? And I told you before, I recommend always that you use this expression of dy by dx of Leibniz. The derivative of the numerator is cosine x times the denominator without change, minus the numerator times the derivative of the denominator. One is 0 and cosine is minus sine, and you divide by the denominator square. When you manipulate here, you get at the end 1 over 1 plus cosine x. And this is the derivative at any point x of this particular function. Now, differentials. You remember in the first introductory lecture, I said that if Leibniz have done a favor to calculus, is in introducing his notations of dx and dy. Now, dx and dy, usually they are found as a quotient by itself, dy by dx. There is no such dx alone and dy alone. Of course, there have been some trials or to find a way to compromise in the middle of 20th century by a topic called non-standard analysis, but this is not our business now. The idea is that differential, they don't exist alone. But then Cauchy himself, a French mathematician who have introduced the limit, has found a way to work out with differentials. And these differentials, in fact, are so efficient. I remember when I was a student, we used not to use differentiation, but because in engineering, you introduce these small increment of dx and dy, and Leibniz has found a way of finding the derivative using these differentials by a principle called the principle of neglection. In other words, when you find dx, you leave it. When you find dx squared, you cancel it, and you can obtain the derivative very easily. And not only that, but he was able to transform the calculus, which is subject related and incorporated in analysis, which is the second science in mathematics, to entangle it from analysis. Of course, is in smaller in elementary applications by transforming into algebra. For here, for example, you have dy by dx is equal to this. Dy by z times z by du times du by dx. You can cancel out this to obtain dy by dx. Here again, look at this. Dy by dx is equal to 1 over dx by dy. D by dx to this, you multiply d by d to get d to the power n. And you multiply dx by dx to get this. Look at this. Look, it's all as if you are manipulating algebra. And that's the astonishing thing about and the beautiful thing about differentials. Here again, d of xy. You get x dx plus y plus dy minus xy, and then you discard dx dy to obtain this. If you wish to calculate dx of y by dx, what you do, you divide by dx. And here, d of y square, you do the same thing, and you discard dy square. You get y square, cancel out with y square. Here, you cancel this out, and you get do dy by 2y dy by dx. So all you do is algebra. Calculate dy by dx if y is equal to x e to the power x. The same thing. You add up dx with every x, and then you subtract the original function. And you work out your algebra. And at the end, what you do is that you end up with this expression here. And if you want to divide by dx to get the derivative, you cancel out dx here, and you get this expression. So differentials you can work out with very easily, like you do algebra, and you get the differentiation of functions. Now, the thing is, which is important, is that we have to summarize our lecture by saying that differentiation means the rate of change, and this rate of change changes at every point. If the function is linear, the rate of change is constant. But in all applications, where engineering, economics, physics, etc., you always find a function which changes all the time. The behavior is not linear, and this is in most real-life applications. So if you want to obtain the derivative, the rate at which this function changes, what you do is you take the increment of the change in y divided by the increment of the change in x, and this is what you get. It's called the rate of change after you take the limit. But you have to memorize something very important. If you want to calculate the derivative at a particular point, you don't calculate the derivative at any other point x, and then you take the limit when f dash tends to of x when x tends to this particular point y. It is true all the time, provided that f dash is continuous at that point, and it's not always the case, because we have shown two examples in which f dash of x was not continuous at the point, and therefore you cannot rely on the derivative in general in order to calculate the derivative at this particular point. This is a nice applet here again, which gives you how the derivative is obtained. Here you have a function. For example, you can move this here, and you want to calculate the derivative. In other words, the slope of the tangent when you have here a secant. These 2 points are a secant, but when this point coincides with this point, then you have a tangent, and that's the idea of the rate of change. The rate of change is the change in y divided by the change in x, but when the 2 points coincide together, and this you get the differentiation, the real differential or differentiation at this particular point, and this is called the derivative. So the derivative is the rate of change at a point, or the slope of the tangent at this point, when you take any secant and you let the 2 points between 2 points, and you let the 2 points overlap or approach together until they coincide, then only you get the derivative at this particular point, and this is what you call the rate of change. Now, with the end of this lecture, we have exposed the subject of differentiation, which is the first subject in calculus. And now we can move later on in the next lessons to applications of this concept here. And until we meet again, I thank you for your attention. And again, wish to remind you that all these lessons are uploaded to the site of the Tunu Telematic University. And I wish you success in your study. Until we meet, thank you for your attention.